Hello my dear, welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, faculty, Department of Mechanical Engineering. So beta, today I will discuss with the continuity of the entropy. So what we will discuss already, we'll discuss that the entropy is a property, that means change in entropy either for reversible process and irreversible process, they are same, but the defined entropy, the change in entropy is defined cyclic integration of dq by t only for the reversible process. Okay. Now, so that we will discuss already through a Kelvin Clausius inequality. Now today we will discuss something about that. What is that, beta? See, so we have to already discuss about that. What is that? See my dear. Okay. So we can say that cyclic integration okay, cyclic integration dq by t. And what is the dq? dq is the heat transfer. dq is the heat transfer. Infinitely small heat transfer, and T is the temperature of a boundary across which this heat will transfer. Okay, and this have a two inequality, that is first is either this is 0 or either less than 0. There I have a two meaning. This quantity cyclic integration is equal to 0 or less than 0, and we know that when it is 0, when it is either internal reversible or a total reversible. Mind it, beta. Sometime this will write like that: dq is equal to cyclic integration of dq by t, and here is right, here you have to see internal reversible, then this is 0. This you have precisely known. Okay, this you know. Okay, this you know. So what is the mean by this one? I will discuss here. What is the mean by this one? So we'll discuss here why we can write internal reversible precisely. Okay, why we can write internal reversible precisely. My dear, if we analyze the four cases, either heat engine, work producing or work absorbing device, in that if we talk about the reversible heat engine and if we talk about the irreversible heat engine, how to make reversible or how to make irreversible. If you make a reversible heat engine, there is a internally as well as externally. That means there is any internal reversibility within the system, and there is no externally irreversibility due to the heat transfer. That means heat transfer across a finite temperature difference, and also the internal engine inside the system there is no any irreversibility. So that is called reversible, total reversible. How to make that engine is irreversible? So the engine we make irreversible is due to the internally irreversible. Mind it. So if you make engine with a very important engine or any device is a irreversible, if you make engine irreversible, that you have must be internally irreversible. This is very clear. Internally irreversible. That means internally irreversible and externally reversible. So the total, as a total, it is a irreversible. Yes or not? Total, it is irreversible. So there must be internal irreversible and external reversible so that the engine is irreversible. Now, so for the irreversible engine, this is less than 0. That means this is a less than 0. It must be internal irreversible and external reversibility. So either reversible heat engine, I am repeating, this is very important, I am telling you. Either heat engine is reversible or irreversible, the external it is a reversible. If you talk about the engine, it is a reversible, working on a reversible cycle, or an engine working on an irreversible cycle, there must be external reversible. This is fixed. Okay. Now you make the engine reversible. There must be internal reversible. Why? Because this is fixed. Either you talk about the reversible engine or you talk about the irreversible engine, this internal irreversibility is fixed. That means the internal irreversibility and external reversible is fixed. So don't bother about the external reversible. All the cases, the externally there is a reversible. Only the reversibility is vanishes, converted into irreversible. Only you have to change the internal phenomena. That means if you make the engine a reversible, it must be internal reversible. Why? Because already it is an external reversible. So if the engine make as a reversible, it must be, it is visible, must be internal reversible. Internal reversible. It must be internal reversible. So at that sense we can write here. Internal reversible, it is external reversibility is fixed. Or you can write total reversible, or you can write total reversible. That total reversible sometime called reversible process, reversible cycle. Okay. So in this sense, if you write this is equal to 0, that means what you can write? You can write like that, the equality in a clauses for just for internal reversible or total reversible. This is clear. This is clear. Now, this is right when there is a irreversible process. Irreversible process. And how to make irreversible process? Irreversible process, that means it must be internally irreversible. It must be internally reversible. That means internal reversible must be internally irreversible. So we talk about the internal sense. We talk about the internal sense. Okay. So we can write like that. Okay. Now for the process, this is for the cycle, and what we see that for the process, if this is your process, and if you want that the process during process 1 to 2 dq by t is equal to delta S is equal to S2 minus S1. Okay, what is this means? That means there must be internal reversible. Internal reversible. This is okay. This is for the process, okay? Internal reversible process. Now, if we have successfully completed that, what mean by the internal reversible, why we write intuitionally here. If you see any standard book, there must be written here internally irreversible rather than the reversible process. What is the motivation? This is your motivation. This is very important, I am telling you. Okay, this is your motivation. Now, take a special case. What is your special case? See, my dear, take, this is your observation, take reversible adiabatic process. That means reversible plus adiabatic process. Okay, reversible and adiabatic. Take, this is your process, reversible and adiabatic. Already you heard about this process when we are discussing about the Carnot cycle, okay? So, what is the reversible? So, for the reversible, right, we know that. So, this is a reversible, okay? So, for the reversible, we know that cyclic integration dq by t is equal to delta S. That means S2 minus S1, okay, no problem. Okay, no problem. And for the adiabatic, what we know that heat transfer across the boundary is 0. If you take both as a combined, add, so what is that? This is 0. That means delta S is equal to S2 minus S1 is equal to 0. That means S is constant, entropy is constant. When entropy is constant, that is called, this is called isentropic process. This is called isentropic process. Hi Sita, how are you? This is called isentropic process. That means if the system exists in a reversible manner, and precisely this reversible in which sense? It must be internal reversible. It must be internal reversible. Okay, it must be internal reversible. Must be internal reversible process. That means, yes, Ishita, I am also good. Your reply, what you reply, your reply always motivate me. Okay, so stay tuned with me. Okay. Now, that means it is not necessarily that isentropic process must be reversible adiabatic process. This is very important. See beta, if there is a adiabatic process, so adiabatic process, that means heat transfer is 0. This heat transfer 0, either any process, either reversible or irreversible. Now, when the heat transfer during a reversible manner, then this is the isentropic process. Okay, but the isentropic process need not be reversible adiabatic. This is very important. I will discuss you a few moments later. Okay, so this is the isentropic process. No problem at all. Now, if you draw the Carnot cycle, already we draw the Carnot cycle on a PV diagram. Now that PV diagram will convert into temperature and entropy diagram. Let's see. Carnot cycle. Carnot cycle. This is very important, I am telling you. What is the Carnot cycle, beta? What is the Carnot cycle? Carnot cycle is a example of a reversible cycle. It must be internal reversible, okay? It must be internal reversible. So, if you draw the Carnot cycle on a PV diagram, so this is your P and V diagram, okay? Now, what is that? There is a one process is reversible adiabatic compression. What is the reversible adiabatic compression? That means you compress the gas in a reversible manner, that means quasi-static manner, very slowly. If you compress the gas very slowly, its internal energy will increase, ultimately its temperature will increase, but you don't allow the heat, energy will transfer as a heat from the system to the surrounding. That means if we increase, that means adiabatic compression, this is your adiabatic compression, this is your adiabatic compression, okay, this is your adiabatic compression. Now, what is that? There is a, now if you compress it adiabatically, now it's allowed to expand at a reversible isothermal process. So now it will allow to expand in a reversible isothermal process, okay, no problem. So this is your expansion, so pressure will reduce, volume will increase. So this is an isothermal process, okay. Now after that you expand again, this is your expansion. Now you expand again in a reversible adiabatic process, okay. So you expand, okay, you expand in a reversible adiabatic manner, okay, you expand. Now you compress it in a reversible isothermal process, so you compress it, now you compress. So this is your Carnot cycle, okay, this is your Carnot cycle, okay. So this is the process 1 to 2, 2 to 3, 3 to 4, 4 to 1. So this is the cycle, and that cycle working on a two temperature limit, high temperature limit and low temperature limit. In this cycle, there must be, there is a heat addition, there must be a heat addition QH, there must be a heat rejection QL, okay, and in this there is a reversible adiabatic compression and expansion. So these two are reversible plus adiabatic compression, okay, reversible adiabatic process, not compression, this is compression, this is expansion. So you can write reversible adiabatic process, okay. Now, if we draw this curve on a TS diagram, T and S. So in this sense, this area, that means what is the area represent within this curve? That is your network, W net. And if there is a cycle, so cyclic integration of W net is equal to cyclic integration of W heat transfer. Now, if we draw a TS plot, so these are the reversible cycle. So for the reversible cycle, what we know that dq by T is equal to ds. We know that for the reversible cycle, we know that. Okay, no problem at all. Now, first process is a compression process. And what is the compression process? Reversible adiabatic. Now, once we compress reversible adiabatic, so what is the reversible adiabatic? Just now we seen that. Reversible adiabatic, that means entropy is fixed. That means 1 to 2, if we move from 1 to 2, in this sense, entropy is fixed. S is equal to constant. S is equal to constant. It is must be, okay. So in this manner, entropy is constant. Now, whether the entropy will increase or decrease, that is the matter. Now, see, this is our 1 to 2. Okay. Entropy is constant. That means here S1 is equal to S2. No problem at all. Now, we move upside or downside. Please reply in the comment box. We move upside or downside. Let's check. Let's check. So, beta, we know that dq is by dt is equal to ds. Okay. Now, during the compression, what you do? During the compression, what you do? You add the energy to the system. You add the energy to the system. Yes or not? During the compression, what you do? That means there is a piston cylinder arrangement. There is a piston cylinder arrangement and you compress it. If you compress it, you must be add the energy to the system. If you add the energy to the system, system must be increase the energy. And there is a adiabatic, that means you are not allowing the energy transfer from the system to the surrounding. From the system to the surrounding. That means beta, what is that? There is a no heat. You are not allowing the heat transfer. You are not allowing the heat transfer. So this is this one. Okay. You are not allowing the heat transfer. Okay. Now that means, see, you are not allowing this heat transfer. So ds is equal to 0. That means entropy is constant. Now the temperature will increase or decrease. Now if you don't allow the heat transfer from the system, reversible and adiabatic process, this system entropy is constant. This system entropy is constant, but you add the energy. This addition of energy will increase the system temperature. Why? Because you add something, you add the energy to the system during the compression. That means you are giving the energy to the system. So system energy will increase, and that energy will increase in the form of internal energy. Why? Because we know that, what is that? dq is equal to du plus dw. Yes or not? Now in this case there is no heat transfer. So in this case there is no heat transfer. So what is that? dw is equal to minus du. Okay. Now this dw is a compression. This is a compression, na? So this is must be negative. So this negative is negative. That means during the compression, what is the work will change its internal energy. That means U2 minus U1. And if you add this one, this will be greater than 0. That means its internal energy will increase, and that increase the internal energy will be, internal energy is the best representation of the temperature, so its temperature will increase. So we have to move from upside. So this is your process 1 to 2. Temperature will increase at a constant entropy. So this is your 1, this is your 2. Okay? So energy will increase. Now 2 to 3 is a reversible isothermal process. What is the 2 to 3? 2 to 3 is the reversible isothermal process. That means, see my dear, isothermal process, that means temperature will constant, but that constant will move. So our movement is at a fixed temperature, TH. So we are moving in from 2 to right side, yeah, 2 to from left side. That is the question. We are moving from, it is a 2, that means end of the reversible compression. Now we are moving at a constant temperature in right side, yeah, left side. That we will discuss. Okay. So during the isothermal process, heat will transfer, but there is no any work transfer. Heat will transfer, but there is no any work transfer. Or you can say that dq by T is equal to ds. Okay. Now in this case, beta, you add heat. Yes or not? You add heat to the system. So this is your positive. Yes or not? this is your positive. You add the system. Heat will add to the system. So it is positive. And it is absolute temperature. So it is always positive. So this positive will increase the entropy. Will increase the entropy. That means S2 will increase than S1. So we have to move, must be 2 to 3 like that. 2 to 3. That means entropy will increase. Now 3 to 4. 3 to 4 must be reversible adiabatic process, but there is an expansion. So there is a expansion. That means during that temperature will reduce at a constant entropy. Temperature will reduce at a constant entropy. So this is your 4. Now 4 to 1 heat rejection. That means this is a negative quantity. Heat will reject. That means this is a negative quantity. So if this is a negative, ds will be negative. ds will negative. ds will negative. That means it must be reversed in this direction. So this is your process and this is your cycle. This is your TS plot. So what you observe here, beta, the system entropy, ds is what? ds is the system entropy. The system entropy may be increase, may be decrease, or remains constant. System entropy will increase when you add the heat. System entropy will 0 when there is an adiabatic process. That means there is no heat transfer. System entropy will decrease when there is you reject the heat. That means in this case you add heat. That means system entropy will increase. In this case reject heat. So system entropy will decrease. In this case there is no change in entropy. That means in 2 to 3 delta S greater than 0, 4 to 1 delta S less than 0, 1 to 2 delta S is equal to 0, 3 to 4 delta S is equal to 0. So the system entropy may be increased, may be decreased, or remains the same. This is locally. This is locally, but you take system or as well as surrounding, system entropy never decrease. That is called principle of increase the entropy. This is very important. That means what do you think here? So this is your Carnot cycle. Now if you find the efficiency, very simple. If you find the efficiency, so what is the efficiency? 1 minus, you know that QL by TH. QL by TH. And what is the QL? QL. This is your QL. Na? This is your QH. This is your QH. And this is your QL. So QL is what? Area under the curve. That means what is the area under 4 to 1? That is QL. What is QH? Area under the curve. That means area under the curve 2 to 3. Area under the curve 2 to 3 is QH. Area under the curve 4 to 1 is QL. So 1 minus what is QL? QL, this is what beta? This is your S3 is equal to S4. So this is your delta S, yes or not? This total is delta S, okay? So what is the area for the QL? For the QL, delta S into this height. What is this height? TL. What is this height? TL, yes or not? What is this height? TH. So 1 minus what is QL? Why? Because we know that Q is equal to TDS. Q is equal to TDS. That means you can write also dQ is equal to TDS. That means del Q, yeah, you can write Q is equal to T delta S. Yes or not? Q is equal to T delta S. So QL. So QL is equal to TL into DS is same for this one, DS delta is, and for this one delta is same. So delta is same. Only the difference is if you write QL. If you write QL, so what is the area? TL into DS. TL into delta S. What is the area of this one? TL into DS. That means TH into DS. So this DS cancel. So what is the efficiency? You can write like that. Efficiency is equal to 1 minus TL by TH. So this is the efficiency. You can write like that. Okay. Now, so what is the important term? The important is system entropy may be increase, may be decrease, or remains the same. System entropy remains the same, and this is when locally, not globally. That means for the system locally, at a local, if you take system plus surrounding, take system plus surrounding as a whole, as a system, as a whole, as a system, that is called globally. In that condition, system entropy greater than equal to 0, greater than equal to 0, greater than equal to 0, that is never decrease, never decrease. This is called entropy principle. This is called entropy principle. So that is a system. Which system it is called? Which system it is called? Isolated system. Okay. So we already discussed that for the isolated system, system entropy may be increased or a constant. This will increase if the interaction is irreversible manner. It is 0 with interaction is a reversible manner, but it will never decrease. But this is called globally. But locally, the system entropy may be increased, may be decreased, or remains the same. It is clear? It is clear, everyone, please? It is clear, everyone, please? Reply in the chat box. Reply in the chat box. It is clear? It is clear, everyone, please? Reply in the chat box. If it is clear, then reply in the chat box. Okay. Now, we take one observation. What is that? What is that? What is the observation? That means, what is the observation? A system undergoes in a state from 1 to 2. If there is a system and the system state will change 1 to 2 by number A, reversible manner, and number B, irreversible manner. They are asking that change in entropy of the system is greater in the case of B. That means if we take this change in entropy of a system of a process A and of the process B, then this says that change in entropy of a system B is greater than change in entropy of a system A. Whether this is true or false, this is true or false, just tell me. Whether this is true or false, anyone please. Whether this is true or false. Whether this is true or false, this statement is true or false, please tell me. That means a system undergoes a change in a state from point 1 to point 2 by a reversible manner, that is delta SA, and irreversible manner, that is delta SB, and he says that, they says that delta SB is greater than delta SA, whether this statement is true or false, please. Whether this statement true or false. See my dear. If this is our T and S, okay, if this is your T and S, okay, so what is the question? A system undergoes a change in state from point 1 to 2 in by a reversible manner, that is delta SA, and a system undergoes 1 to 2 by a irreversible manner, that is delta SB, and the statement says that SB is greater than SA, whether this statement true or false. So there is a system which is at state 1 will go to the state 2. By the 2 process, one is the irreversible manner, one is the irreversible manner, that is B, and other is in a reversible manner. Other is in a reversible manner, please. A. So whether the entropy change of SB is greater than the entropy change of SA. See this. This is your S1, this is your S2, so this is your delta S. See my dear, delta S is same or differ? No, it is the same. That means this is false. This is false. Why? Because entropy is a system property like other property, and that property is a path independent. That means change in entropy S2 minus S1 is applicable for any process. Applicable for any process, whether the process is reversible or irreversible. Okay? So this is clear? Now, if this is clear, so take the other one. That is very important. Take the other observation. Take the other observation. Okay. Now, what is the observation? See my dear, the equation we can write here, dq is equal to T ds. Okay. this equation is valid for which process? This equation is valid for a reversible process. Yes or not? Yeah, internally reversible, yeah, reversible. This is for reversible process, and this is for, and this is a second law of thermodynamics. Okay. This is your second law of TT. Okay, this is for the reversible number first. What is the number second? If we write like that, dq is equal to dE plus dW. If you write like that. So this equation is the first law of thermodynamics. Yes or not? Of thermodynamics. And what is the useful of, what is the application of this first law of thermodynamics? And if you write dW is equal to P dV, this is for reversible process. This is for reversible process. This must be reversible. That means internally reversible. That is the internally reversible. Must be internally. That means this process follow the quasi-static process. Okay. Quasi equilibrium process for any type of the system, either close or open, either close or open. Okay. Now, if we write dq is equal to du plus p dv, what is the equation? What this equation represent? This is for the closed system. This is also for the closed system. Yes or not? Why? Because only transfer is the heat and work, no mass transfer. So precisely this is for the closed system. This is for the closed system. This is also for the closed system, but along the closed there is a stationary system. Why? Because we neglect the kinetic and potential term here. This is the total energy. This is the total energy of the system. Total energy of the system. And that total energy of the system is intermolecular energy, kinetic energy, and potential energy. If we disregard the kinetic energy and potential energy, that system is called a stationary system. So this equation is valid for the closed stationary reversible process. This is for reversible process. So this equation is for the closed system, for closed system is closed. Why? Because only heat and work will transfer. Closed system, and only valid for reversible process. Only valid for reversible process. So this is for the reversible. Now start with this equation. So we have dq is equal to du plus p dv. Okay, p dv. If you write, so this is your u. Okay, p dv. Now, so this is for the first law of thermodynamics, applicable for the closed system and the closed and stationary system. Why stationary system? Why? Because we disregard the kinetic energy term and potential energy term, and this is for the reversible. So reversible is there or not, this will defined by this work transfer. Okay, this is work transfer for the reversible manner. Now, so for the reversible, what is dq? TdS. This is TdS. Okay, and what is du? And what is this? PdV. See, my dear, TdS equal to du plus PdV. This is your TdS first equation. TdS is equal to du plus PdV. What is the validity of this equation? This is very important. This is for any process. And this is for reversible process only. So while we are deriving this equation from this equation, so you have to confuse that, okay, sir, this is for the reversible, so this is also for the reversible. Why? Because dq equal to TdS for the reversible, PdV is the reversible, so this is for reversible. No, why? Because this is a property relation. T S2 minus S1, U2 minus U1, P V2 minus V1. So these are the property relation, like PV equal to MRT. PV is equal to MRT is also property relation. So this is the property relation. So this property relation will, this equation will independence of the path. So this is for the any process. Yes, it is derived by the reversible manner. It is derived by the reversible manner. Once it is derived, it is applicable for the both process. Like the entropy. Yes, change in entropy for any process, but it will derived for the reversible process dq by t. While it's derived, that means it is derived by dq by t in the reversible manner. But once it is derived, the change in entropy is applicable for any process. dq by t is equal to change in entropy, it will derive by the reversible process. Once the change in entropy is come, that change in entropy is applicable for the any process. Likewise, yes, this is derived for only, this is derived by the reversible manner. This TdS equal to du plus PdV is derived in the reversible manner. Once it is derived, it is applicable for any process. Why? Because it is a property relation. It is a properties relation. Okay. Similarly, we can write like that, TdS is equal to change in enthalpy dH minus VdP. This is also applicable for any process. This is also applicable for any process. Now there is one observation. What is that? If you have studied this one, so what is the observation? Take this one. Very important. This is important. The student get confused here. Please give me a reply. The change, the entropy of a fixed mass entropy of a fixed mass, that means there is a closed system. Fixed mass matlab closed system. Fixed mass for an ideal gas, that means there is a gas, have a closed system, ideal gas, decrease in every isothermal compression. This statement is true or false? Please give me a reply. That means the entropy of a fixed mass of an ideal gas I will discuss you. First give this answer. Sir, entropy change for the polar tropics, I will give you. that is the polytropic process. I also derived in the previously video lecture. I also derived. We'll take the isentropic process. Yes, entropy will discuss. Oh, acha, entropy. I will think that you have to ask the work. Okay, entropy will discuss for the polytropic process also. The next preceding. First discuss with this. Here, there is no any derivation. There only we here today's only we focus about the what we study today's. That means today's and day after previous classes. That will okay. So first give this answer. First reply this one. The entropy of a fixed mass of an ideal gas decrease every isothermal compression? Yes or not? True or false, please? True or false, please reply in the chat box. Yes. Now, just it is right. Now, sometime in the thermodynamics, what is the dilemma? You have to study and very clearly you have to find the answer, and it is right. But the problem is that how to think. That is the how to think in a certain direction. So in the thermodynamics we have the thinking in many directions, but that direction is valid for all the concept of the entropy or not. That is a very important. So how to say that yes, you are right, it is true. But how? How? It is true. Entropy of a fixed mass of an ideal gas decrease every isothermal compression. This is the isothermal, for reversible. Okay. Isothermal, every isothermal. Yes, okay. Now we'll think that. How to answer this one? See very carefully. We know that for any process, TdS is equal to du plus PdV. Why we are applying this equation? Just think. Fixed mass. That means this is for closed system. This is for the closed system of an ideal gas. We'll take ideal gas. Decrease in every isothermal. Every. So if you think about that for reversible, this is to know. Every. This is very important, I'm telling you. Atul, if you think that only for the reversible, you are wrong. For every, then it is also true. If this is a reversible, it is also true. If there is a, I will write that the entropy of a fixed mass of an ideal gas decrease in irreversible isothermal compression, then also it is true. See. So this equation is applicable for any process, yes or not? Every process. This is applicable for every process. Now, for the, okay, we can write here for ideal gas, na? So we'll take change in enthalpy, no problem, no problem. Minus dP, you can write also. TdS, we can write like that. TdS is equal to dH minus VdP. This is also for every process. Every process. Now, this is not for reversible. This is very important line I am telling you. That's why this is important. Now, for the ideal gas, what is DH? DH is Cp delta T. Why? This is per unit mass basis, specific. Now, this is for, why we can write here? For ideal gas. Ideal gas, okay, no problem. For the ideal gas, this will write. Now, here DH is 0, yes or not? DH is 0, why? Because, why? Isothermal is 0, why? Isothermal. So this quantity is vanishes. DH is vanishes. So what is the equation? ds is equal to minus VdP by T. See, my dear. Okay? Okay? Now, This, see, specific volume, this is positive. Volume is a positive quantity. Why? Because this is 1 by density. Specific volume is 1 by density. So this is positive. This is your positive value. Okay. Now what is dP? Increasing or decreasing? It is also increasing. Why? Because there is a compression. During the compression, dP will increase. So this will also positive. Now, this will also positive. Why? Because compression. Now, what is the temperature? This temperature is always positive. Why? Because absolute. So, this all quantity is positive. So, ds will always decrease. Always. So, my dear, very important. You don't confuse. If there are two statements, why the confusion is created here? If I am asking you the entropy of a fixed mass of an ideal gas decrease in reversible isothermal process, number first. The entropy of a fixed mass of an ideal gas decreases in irreversible process, irreversible isothermal compression. Number second question. Entropy of fixed mass for an ideal gas decrease in every isothermal. All the statements are true. That is the beauty. It is not stick for the reversible. Mind it. That's why this question is very important. That is the beauty of a thermodynamics. You are thinking, you are giving a right or a wrong answer. It is true. But what is the background? That background you must have developed during the study of thermodynamics. That is the beauty of thermodynamics. Okay. Okay, beta? This is clear? This is clear? This is clear now? Now, we take the another observation. Just tell me. What is that? What is that? Constant pressure line that means there is a constant pressure line on which drawing on HS diagram the HS diagram also called a molar diagram. Mind it, beta. Molar diagram always positive. Always positive. Please, true or false? True or false? Reply in the chat box. This is true or false? A constant pressure line on HS diagram always positive. True or false? Please. This is true or false? Please, everyone. This for everyone, please, true or false? See, beta, we know that TdS is equal to dH minus VdP. Yes or not? Okay. Now, this is your constant pressure line. Pressure is constant. That means this is 0. Why? Because pressure is constant. Okay. Now, so what is that? dH by ds at which line? Constant pressure process is equal to T. Okay. Okay, this is clear. Now, if we draw HS diagram, this is H and S. So, dH by ds is the slope. dH by ds is the slope of which line? Constant pressure line. So, HS diagram, and this is your saturation curve, and this saturation curve, this is your critical point. This is your critical point. Now, see my dear, constant pressure line, and this T is what? This is the absolute temperature. That means it is always positive. This is your absolute temperature. Now, this is your liquid. This is your liquid plus vapor, and this is vapor. Okay. This is called wet region. In a wet region, temperature and pressure both are coincide. That means you can never, that means temperature and pressure both are independent property, but in the wet region both are dependent property. This is very important. Okay. That means, see my dear, from here, let's suppose pressure line. This is our pressure line. So, this pressure line, at this region, the pressure, temperature, pressure, temperature, pressure, temperature, pressure, temperature is same. That means, see, while we are going in this direction, this is very important, my dear, observation. While we are going from this side, the line is inclined. A straight line with inclination. See, there must be inclination. Why it is inclined? Why? Because we are going in this direction, we are adding the heat. And once we are adding the heat, but we are adding the heat, which heat? Which heat? Latent heat. But during the latent heat, there is no any temperature change. So, the temperature, this one and this one is same. At any point we take temperature is same. So, the slope is constant. So, each and every point the slope is constant. There is no any changing of the slope. There is no any changing of the slope. But you increase the heat, you are giving the heat, its enthalpy will increase. So, the enthalpy at this point and enthalpy at this point are differ. That means this is the line over which the same slope is there. So, it is a straight line. But while you are giving the latent heat, this point is higher than this point. See, this H2 value is higher than H1 value. Why? Because straight with the same slope but higher enthalpy. Why? Because you are giving the heat. Okay. Now, if we shift upward, that means if you shift upward at a different temperature, that means if you shift the upward at a different temperature, the slope is also same, but that slope is higher than this one. This is very important, I am telling you. That means, if you draw this line, this is look like that. It is not parallel. This line and this line is not parallel, I am telling you. Why? Why? Because this is higher temperature. This is lower temperature, this is higher temperature. So, if the temperature is high, the slope of this line. So, if we write this is the slope theta, so at this point this theta is large. Why? Because this is higher temperature. but that temperature is maintained throughout from this point to this point. So the constant slope. Constant slope, higher, constant temperature, higher slope. In the wet region, constant temperature with higher slope. If you increase from top to bottom to top up to critical point, the slope will increase. Why? Because this is the higher temperature. If the temperature is high, slope is high. And these all lines are constant pressure line. The pressure is same. Temperature is same. At this point, temperature, pressure same. At this point, temperature, pressure is same. But that temperature, pressure is higher than this one. So slope is high. Okay, now. So if the slope is high, so this will move like that. If the slope is high, this will move like that. So it is a like that. So in the superheated region, what is that? In the superheated region, here these lines are constant. There are many observations. What is that? First observation is that within the wet region, the line is straight. Number first. Within the wet region, the line is straight. But the upper line have a more slope as compared to lower line. Why? The upper line have a high temperature. Upper line have a high temperature. But this high temperature is constant throughout at a constant pressure. So this will slope straight line with the higher slope. So this is lower slope, this is higher slope, like that. Now, this is a vapor region. So if you want to increase the enthalpy, that means if you add the heat, so this is not a constant temperature, this is the constant temperature line. This is T1 is equal to constant, this is T2 is equal to constant only between this point to this point, this point to this point. But this T2 is not constant throughout. That means in the superheated region, this slope, this line, if you extend this line, see my dear, if you extend this line, this is your line. If you extend this line, this is your line. So, see, after in the superheated, T1 slope is sudden increases and there are continuously increases. Here it is increment are same, but here increment are continuously increases. Why? Because you are adding a sensible heat. During the sensible heat, temperature will change. That means here temperature is lower, here temperature is higher than this one, here temperature is higher than this one, here temperature is higher than this one. So the slope is continuously increased. But now, so there is a T2 temperature, high temperature. Now you add the heat to the high temperature. So the rate of increment of the slope of this one is higher than this one. So the rate of increment, so this is the rate of increment of the slope and this is the rate of increment of, so this point is temperature is, and this point is higher temperature than this one, this point is higher. So the rate of increment of the slope is higher, see. So this is true, always positive, either in wet region or either in superheated region. So constant pressure line on HS diagram, so this is your P1 and this is your P2. So constant pressure line on HS diagram always positive, either it is in wet region or either in superheated region. But what is the difference? In the wet region, the slope is fixed, but in the superheated region, the slope will increase. But the slope is fixed, but if you increase the temperature, slope will increase. But that increment of the slope is constant in the wet region, but in the superheated region, the increment of the slope is continuously increasing. Why? Because you are adding the heat, so that that heat will add in a sensible heat, and that sensible heat will continuously increase the temperature. So this is the Mollier diagram. It is clear, everyone, please? It is clear, everyone, please? Reply in the chat box. It is clear, everyone, please? Reply in the chat box. It is clear, everyone, please? Reply in the chat box. Okay? So up to that, we'll stop here. After that, we will discuss continuously from the next preceding lecture. Okay? Thank you. Bye-bye. you.